Okay, so the CCD sensor is made of silicon. It works based on the photoelectric effect, and it's comprised of an array of pixels. On the other hand, the CMOS sensor is made of silicon. It is based on the photoelectric effect, and it comprises an array of pixels. So maybe we need to dig just a little deeper, because on the surface they're exactly the same thing. Let's start out with how the thing works. The first part is the photoelectric effect. This is an effect that was actually explained by Albert Einstein before he figured out the theory of relativity. In fact, that's what he got his Nobel Prize for, not relativity. And what happens in a photoelectric effect is a photon of light hits a piece of metal and knocks off an electron. This is normally done in a vacuum, so you can collect the electrons. And he explained how all this works in a quantum mechanical sense. In a silicon sensor, it's a little bit different. It also exhibits this photoelectric effect where a photon comes in, hits an atom of silicon, and knocks off an electron. But because photons can actually penetrate into the silicon, the electrons are actually released inside the crystal. They're not released out on the surface like they are with a metal. Both CCD and CMOS sensors use ultra-pure silicon as a detector. Now, silicon is a very interesting substance because it's what's called a semiconductor. And you can play with its electrical properties very simply by adding little bits of contaminants in there, basically, a different atom. So in this case, this is a germanium crystal with an atom of arsenic stuck in there every so often. And arsenic's a very similar material to germanium, but has a different number of electrons. And so what this does is it has an extra leftover electron, and it actually can roam around in the crystal. The same way electrons will roam around inside of a metal. So it makes the material suddenly changing from a very good insulator into a pretty good conductor. Same thing with a p-type material. In this example here, we have silicon atoms, and we've stuck an atom of aluminum in here. And the aluminum doesn't have an extra electron, it has a missing electron. And that missing electron, what we call a hole, can actually wander around the crystal too. And this lets current flow inside the semiconductor. So we've changed it from being like an insulator into being more like a metal. Now the fun part comes when you butt up a N-type and a P-type material together. So this is the simplest type of semiconductor device. We've butted up together a P-type and N-type region. And in fact, it's usually made in a single crystal. We just stick the extra atoms in. And what happens is they cancel out. The electrons and holes in this middle region called the depletion region, they all cancel and no current can flow. So no current can flow through this device. But if you add more electrons over on one side and more electrons over here and more holes over here, by attaching a battery, you can actually make the current flow because it shrinks the depletion region and current starts to flow. If you turn that battery around, current doesn't flow. This is what's called a diode. So it's the simplest switching device. Now, if you make more complex structures, for example, PNP or NPN, this is what's called a transistor, which is an electric switch. More commonly, though, these days, we actually use what's called a field effect transistor. I should also mention that we can take the silicon dioxide wafer, dope it with these NMP-type contaminants, and then add aluminum or copper tracks, and we make a whole circuit on a single piece of silicon. So this is how all modern electronics are built. And most of the electronics have to be designed in a package where light can't get into it, because if light gets into the package, it will actually start turning all the switches on. And it actually interferes with the operation of your electric circuit. An optical sensor, on the other hand, you deliberately, instead of having a metal or plastic cap on it, you actually have a piece of glass. And that allows the light in, hitting the silicon, and generating photoelectrons inside the silicon. So both the CMOS and CCD sensors take advantage of this characteristic silicon. So the fundamental performance of the detector is the performance of silicon. And that if you make your sensor as good as it can possibly be, it will be limited by the silicon. So it really comes down to how close you can get your design to be the optimum performance of the silicon detector. So what is the difference? Well, let's talk about the CCD. This is a charge-coupled device. That's where the CCD comes from. And basically, the pixels are defined by oxide insulator and wire electrodes. So there's a layer of silicon dioxide here, which is an insulator. And then there's electrodes on top. And they have, some are positive and some are negative. And the light goes through these electrodes into the silicon and generates photoelectrons. A photon hits the silicon, knocks off an electron, and it's free to roam around. But because there's a positive charge up here, the electrons are attracted to it. So they head up towards the positive electrode, but they can't get through the silicon dioxide. So they all sit here, and they collect as you expose your camera to the stars. So during the exposure, they all collect together in these little wells, which are what the pixels are. And then at the end of the exposure, they're clocked out, one packet at a time. And the way this works is those electrodes are changed in voltage. And so it's no longer positive, now it's negative, and the electrons all chase away across the chip. And you just keep cycling the electrodes and the pixels cycle across the chip to the bottom, where they run horizontally out the side, and they all come out in a single readout register in one corner of the chip. So the big advantage of this is that one single amplifier that's doing everything is doing the exact same thing every time, so it's extremely consistent. You get the exact same characteristic for the readout of every pixel in the array, because it's the same transistor reading out every pixel in the array. It does have the disadvantage of being slower because all the charge has to be clocked out to the bottom corner of the array. So some CCDs are actually designed with multiple readouts, and they may be in all four corners in some cases, and they all clock out in 4 different directions. That's just to speed it up. Now, once you get the charge at the output node of the CCD array, it's read out and presented as a voltage. And that's read by some electronics. They use an analog to digital converter to turn that into a number, your ADUs that you're used to seeing on your computer. There's actually some more fancy electronics in between there. They have a thing called a correlated double sampler, which basically every time you dump a pixel in, you have to throw a charge out. So there's a reset circuit that throws it out. And then you measure the leftovers, because the reset isn't perfect. And then you dump the new charge in, you read it again, and you subtract the two. And that gives you just how much you dumped in. Because there's some noise associated with resetting it. You can't perfectly reset it every time. The laws of physics are actually in the way on this one. But we can scoot around the laws of physics by being clever about our circuit design. So the circuitry for the CCD is kind of complicated, both because of all those fancy readout electronics, and also because the clocks, all these electrodes going across the chip, all require really weird voltages. The most complex CCD chip I've ever seen, the KEI 10100 rather, from Kodak, now on semiconductor, has 11 vertical clocks, which are all 3-state voltages, and then about half a dozen horizontal clocks. So that's what, 17 different pins on the chip that you have to cycle with different voltages. So there's a lot of electronics that drive this chip. So that's a disadvantage of the CCD. The advantage is the extreme consistency of the CCD. Now, CCDs are not perfect devices. They have various problems. And one of them is you have all these electrodes that are going across the top of the chip. And they block light. Now, people have made technology to make the electrodes more transparent. But the fact is they still absorb or reflect some of the light that comes in. So a lot of manufacturers have now come up with these micro lenses. And what they do is they take the light coming into the sensor and they direct it into the photodiode, the actual sensor area, so that all the surface of the chip is now sensitive to light, or as much as possible. And that is what we call fill factor. How much of the front of the chip is actually sensitive to light? And so these micro lenses help with the fill factor. They improve it. Again, transparent electrodes. There are various different kinds of CCD sensors. There are full frame sensors where all the charge is actually clocked out from pixel to pixel on its way out of the sensor. You actually need a mechanical shutter to cover it during that readout. Otherwise, the image will blur as you're reading it out. There are also what are called interline and frame transfer CCDs. Interline CCDs, for example, have a row of unsensitive pixels between all the sensitive pixels. And then at the end of the exposure, all the pixels jump half a pixel over, and they're covered up by this barrier made of aluminum that's on top of them. And now they can be clocked out without any light contaminating them. The disadvantage is now half the chip is taken up with these readout columns, which means that there's less room for electrons, and there's less fill factor, which again is what the micro lenses help with. So there's the reasons for using interline sensors is they eliminate the shutter, and they're faster. So there are compromises in the designs of the sensors. Now the ultimate in sensitivity comes from a back-illuminated CCD. Most sensors have the light coming in from the front. They go through all the electrodes and gates and things into the silicon at the back where they're detected. Now, if you can flip this over and have the light come in from the back, you avoid all that. And so the light just falls directly on the silicon. And it is detected, all of it's detected. There's a 100% fill factor. The disadvantage of this is in order for this to work, the chip has to be very, very thin, like maybe 10 microns thick. So what they do is they build it this way first, and then they flip it over, and they polish off the back of the chip. And since 10 microns is very, very thin, if you go a little too far, you have no chip left. And if you don't go far enough, it doesn't work. So these are very difficult to make, and as a result of that, their production yields are lower, so the costs are much, much higher. So that's a disadvantage of these sensors, but with back-illuminated thin sensors, you can achieve up to 98% photon sensitivity. So you get 100 photons in, and you get 98 photoelectrons out. That is almost perfect for all intents and purposes. So that's why people are willing sometimes to spend the big bucks to buy a back-illuminated sensor, because their performance is incredible. And some of these sensors have been designed to achieve readout noise. Every time you read the pixel, there's a bit of noise in there. They've been able to achieve read noise on the level of 1 or 2 electrons, which is incredible. So think of that. You might have 1,000 electrons in this thing, and only 1 or 2 of them are actually noise, or even 60,000 electrons. The thing is, to get that low noise, you have to read it out very slowly. So a sensor that's capable of this kind of performance is actually pretty slow to read out. So usually they're not really large arrays. But these sensors are, for all intents and purposes, almost perfect detectors. Really super high performance. Another disadvantage of typical back-illuminated sensors is they have to be cooled a lot more to have low dark current. So the cameras tend to be also very expensive, not just the sensors. Okay, let's now go over to the CMOS side and look at how they work. So CMOS is what all our modern electronics are based on. Back in the day, there were various competing technologies, NMOS, TTL, all these different versions of logic gates, and everybody settled on CMOS. And that's what all the modern wafer fabs make. Now, CMOS stands for complementary metal oxide semiconductor. Why complementary? Well, here is a standard CMOS logic gate. It's called an inverter. It takes a 1 in, turns into a 0, or a 0 comes in, turns it into a 1. They have a P-channel MOSFET. So basically, there is a channel made of P-type material, an insulator, and then an electrode gate. And it only conducts electricity either when there's a voltage on the gate, basically. So when you apply voltage on the gate, current flows top to bottom. But there's no actual conduction through the gate. It's actually insulated. So it takes very, very little energy in to control a fairly large amount of current going through. And then at the bottom, they have an N-type. And the idea behind using a P-type and an N-type is they work on opposite voltages. So when you turn one on, the other one turns off, and when you turn the other one on, the first one turns off. So when they're just sitting there, sitting at 1 or 0, there's absolutely no current consumed. So it's very, very low power. It only consumes power when it's switching from 0 to 1 or 1 to 0. So this is a much lower power architecture than what we had in the past, which is why it's so popular. And by making these transistors smaller and smaller, they can go faster and faster, which is one of the reasons why we keep shrinking them. That and being able to cram more of them on a chip. So the advantage of this is higher speed and lower power. It's not necessarily optimum for detecting light, though. The old Ccd sensors usually use NMOS, which is just this type of transistor. And I believe the Sony sensors use PMOS, which are these types of transistors. And that's all that's in there. The CMOS sensors are actually built using obsolete wafer fabs. And so you know, when ON Semiconductor bought Kodak's wafer fabs, they kept them because that's what you need to build Ccd sensors. They can't use the modern factories that are used to make memory chips and microprocessors. They're not compatible with the technology. So that's one of the weird things about CMOS. It's actually obsolete. Or sorry, CCD is actually an obsolete technology in many ways. So CMOS sensors have a lot of advantages over CCD because they're built on the technology that is used to build computers. So they can contain all the components of a computer in there. Also, CMOS is also used for all the analog electronics these days. Much of the analog technology is also based on CMOS. So they can include analog circuits in there as well. So now we have a circuit that not only has the optical sensor, it also can have the converter and all the associated circuitry inside the chip. Another thing is that there's actually a readout amplifier on every single pixel. So there's at least one transistor, maybe a couple, right alongside every pixel in the array. So this means that we can read out the array very quickly. In fact, we can decide we only want to read out these pixels here and not read out those pixels there. So it's really, really fast if we're doing a subframe. So this has a lot of advantages because now we can actually just shuffle out electrons after they've been amplified, and we don't have to worry about being so quiet. CMOS sensor, CCD sensors require very, very low noise electronics because you have to be very careful you don't introduce noise as you're reading them out. CMOS, it already has an amplifier right at every pixel, so it's actually much easier to handle the electrons when they come out. And in fact, there's usually an ADD converter built right into the chip. So you put in 3 volts or 5 volts into the sensor, and out come digital numbers directly from the sensor. So this makes it very, very cheap to build a camera, which is why you will find them in your cell phone. That's why we have CMOS detectors in our cell phone, because the very chip that does all the detecting is the whole camera. So they're faster to read out. They're cheaper to make because they're made with CMOS as technology, and all the interfaces are digital. You can just wire it right up to your computer, and you're done. Now, does that make it better? And not so fast. The difference is that because you have at least one transistor at every pixel, they take up some room. So right off the bat, you're losing sensitivity because your fill factor is worse. It may only be a quarter of the pixel that actually contains sensitive area. So right off the bat, you're throwing away 75% of the light. This reduces quantum efficiency, and it also reduces how much electrons you can store in each pixel. Now, big pixels that are completely used for detecting light can store a lot of electrons. And the limitation here is really how much electrons you can store in a certain volume of silicon. It isn't really any different from a CMOS sensor to a CCD sensor. The difference is the architecture, how much room is allocated for the pixel. And it is always lower in a CMOS sensor. So they don't have as much dynamic range. You can't detect a faint object and a really, really bright object at the same time in the same array because you'll saturate out the bright pixels. Another problem they have with these sensors is fixed pattern noise. Because every single amplifier and every single pixel has its own characteristics, they're all a little different. So you take a picture from a CMOS camera and look at it, and there's a fixed pattern of random noise, but it's the same on every single picture you take. And it can affect the gain of each pixel, not just the offset and such. So it actually ends up being a lot more rough a signal output, a lot more crude signal output than it is on a CCD. And you can do things like calibrating like dark frames and flat fields and things, but it still is harder to make a CMOS sensor as low noise as a CCD sensor. So there's also extra circuitry in there. There's amplifiers, ADD converters, and things, and these do make electrical noise, and this can degrade the performance of the sensor. One thing you often notice on CCDs is the readout amplifier in the corner makes a little bit of light, because every silicon junction is actually a diode which generates light like an LED does, light emitting diode. All transistors do this, and the more you have, the more of this light is emitted. So some care has to be made to make sure that that light doesn't contaminate your image even as you're reading it. One other disadvantage is that the most advanced CMOS sensors, well, let's face it, they're making these for the cell phone market. Sony manufactures 1 million sensors a month. If you can imagine how many astronomical sensors they manufacture a month. In fact, they don't manufacture any astronomical sensors. They do manufacture sensors for industrial and security applications, and the astronomers borrow those for their cameras. On Semiconductor / formerly Kodak actually makes scientific grade sensors intended for astronomy and other low light applications. But the companies that are making these CMOS sensors are more targeted on high volume applications. So they tend to optimize them. Your cell phone has really, really tiny pixels, which makes for a great tiny, tiny camera. But those tiny pixels mean that they can't store as much light, so they can't have as much dynamic range. And the optics for them are also similarly complex because they're so tiny, the pixels. So this means CCDs are better, right? Well, as of today, that is correct. The best CCD sensors today are better than the best CMOS sensors today. And moreover, they are capable on all fronts. They have lower noise, they have lower dark current, they have higher well depth, higher quantum efficiency, but they cost a lot more. The CMOS, where its advantage is in cost for performance. It's a lot more bang for the buck for a CMOS sensor, which is great as long as it's good enough for your application. If it's not good enough, then you're going to have to use a CCD sensor. On the other hand, the CMOS sensors have been improving by leaps and bounds in recent years. So in the early days of digital SLRs, they were all CCD, except the crappy ones. Now, many of the best DSLRs actually do have CMOS sensors in them. So the performance gap has closed a lot. It's a lot less expensive to make a really, really big array, 30 megapixels in CMOS than it is to do it in CCD. So if you want to be able to actually afford the camera, there's something to be said for CMOS, even if the performance isn't quite on a par. Now, the evolution of CMOS, here's a good example. This is the Sony Exmor technology, and I'm going to go a bit over the evolution of this technology over time. Let's start with the basics. They start out by trying to reduce the noise. So the original design had their readout amplifier, Corley double sampler, goes off to an ADD converter in the corner. So that ADD converter converts every pixel. It's not a bad structure. In here, this Corley double sampler is an analog device that, as I said, subtracts the light from no light and calculates just the difference. It was a way of reducing noise. What they've done since then is they've actually added one ADD converter per column, and then had an analog and a digital correlated double sampler to give it better noise reduction. Yes, you can do correlated double sampling in digital domain. In fact, the original ST6 camera did it that way. It did the conversion of the bright signal, conversion of the dark signal, and subtract the two. Most of the modern cameras do this in the analog domain before they convert the signal. But here they're actually doing both, one after another, which does have certain advantages. Once it comes out of the readout column, then all the other circuitry is all digital. And digital circuitry is really easy to handle noise with. So it makes it a lower noise and faster device. So that was a basic first generation of XMOR technology. Now, what did they do to improve it? Well, they started out with aluminum conductors and a certain size of like a 90 micron design rule, and ended up being a pretty tall chip. This is 1 pixel, and the photodetectors are way down here at the bottom, and the light's got to go all the way down there. This would be the micro lens here. So when they went to the copper conductors, they were able to make the conductors a lot thinner, and these are conductors as well. So they were able to make everything thinner and reduce the distance from the micro lens to the detector part. This makes the camera more sensitive. Then they went to 65 nanometer copper and made the thing even smaller. So simply by going to a finer line geometry on their process and using copper instead of aluminum, they were able to improve their econo efficiency and improve the angle at which light can come into the sensor. One of the problems with micro lenses is if the light comes in at an angle, it actually won't hit the pixel. And by making this a shorter distance, they're able to accept a wider range of angles, which means that if you have a very fast lens, you won't cut off the light that's coming from the edge of the lens. Okay, then they actually took a lesson from the Ccd sensors, and they did the back-illuminated thinned. So here's the previous generation, and then they go to back-illuminated, where they flip the chip over. The micro lenses are on this side, go directly into the pixels, and all the electronics are on the bottom. Oh, I should mention that also, because the electronics is underneath the pixel, that means that there's none of it's in the way of the light, and none of it is affecting your volume of the pixel for storing electrons. It improves the dynamic range. And then they have a version of it for near infrared, which is where the silicon is a bit deeper. And the reason for that is that infrared penetrates further into the silicon before it gets absorbed. So they need a thicker chip in order to absorb that. So you can either have a little better visible light performance or better infrared performance, depending on which version of the chip you want to get. So going comparison here, so here's a front illuminated sensor, the metal wiring inside here, the color filters, the lens, and the sensors down here, whereas here it's going directly into the pixel. And the light receiving surface is close to the front of the chip instead of being way down inside the chip. So obviously this is a pretty expensive technology, and they put a lot of money into getting this all to work. And they've used this to go after the cell phone market, which means itsy bitsy teeny bitty little chips that have like 1 or 2 micron pixels. Not very well suited to astronomy, where you might have a 2,000 millimeter focal length. You want to have like a 9 micron pixel, or maybe at least a 6 micron pixel to use on a C8. And a bigger telescope might require even bigger pixels. So the current generation of chips aren't suitable for use in astronomy, even though they have the performance that's much closer to CCD. Also, I'm pointing out here that with the current technology in CMOS, the old ones would have the pixels here and the circuitry here. Now they have the pixels here and all the circuitry underneath it. So it's actually a smaller chip, which means that they can make more of them on a wafer, which means they're cheaper. So again, CMOS is showing its cost advantages. Okay, now for the bad news. Sony has decided to go all in on CMOS, which means they're closing down their CCD wafer fabs in a few months. So everybody who loves those beautiful ICX 694s, they're not going to be making them anymore. Fortunately, Sony did something that was very unusual for Sony, because they tend to do dumb things like, oh, let's cancel the sensor and then come up with a replacement 2 years later. They didn't do that this time. What they're doing right now is they're running their factories. They have 2 wafer fabs that make CCD. They're running them 24/7, all out, making as many chips as they can. And they are storing the wafers, fully tested wafers, in vaults. And then they're getting all the manufacturers who use the chips to put in orders for the next 10 years. In some cases, 5 years, depends on the chip. And they will promise that they'll have those chips for you. And Even nicer, they won't actually force you to buy them even though you put the order in for them. So if you decide no, you don't want these chips anymore, they're not going to force them on you. So Sony's CCD sensors are not dead, they're just dying. They'll be around for another 10 years, but obviously what Sony is thinking here is that between now and 5 to 10 years from now, they're obviously going to develop new CMOS sensors that are going to replace these CCD sensors, and they believe they'll have the same or better performance. So sometime in the next 5 to 10 years, the question will be which is better, CMOS or CCD, and you're going to say, well, they're pretty much the same. And at that point, given that CCD is built on an obsolete technology, requires a lot more electronics to run it, and is a lot more expensive, it's pretty clear the world is going to switch to CMOS. There are some challenges, though. Even so, most of these sensors are made with color matrices, the Bayer matrix, because that's what you need for cell phones and taking quick shots of your friends and family. They are going to be manufacturing some sensors in monochrome. They already are, fortunately. As I mentioned before, the pixel sizes are way too small because they're designed for cell phone cameras. And currently, they have what are called BGA packages. This is the chip. That's the top. Flip it over. Ball grid array. It's an array of balls on the bottom of the chip. That's great for compact electrical connections. Not so great for cooling. How do you cool that chip down? Answer is it's pretty hard. So they're going to have to make a version of this with a pad on the bottom that you can actually attach a cold finger to chill the chip down. So they're making it harder to make a cryogenic camera like we use for our CCDs, where we chill it down to minus 20 or 30 degrees for a low dark current. They're making that difficult. So hopefully they'll make new sensors that don't have this design that will actually be able to properly chill. On the other hand, there is some good news on the CCD front because Kodak invented basically much of the CCD technology that eventually put them out of business and didn't manage to make the transition from film technology to CCD technology, even though they had CCD technology. Companies have a lot of inertia when they're that big. So they went under, basically. They shut down. They sold off all their patents. But before they did that, they spun out their CCD manufacturing line into a company called TrueSense. And TrueSense has since been bought by ON Semiconductor, one of the largest electronics manufacturers in the world. They were spun out of Motorola when Motorola decided to go after the cell phones themselves. So they're actually a very respected, very huge company, and they have bought a lot of imaging companies that make different kinds of sensors. So they have a huge portfolio, a whole bunch of engineers from different companies originally who have different ideas about how to do image sensors. They put them all together into one division and said, talk to each other, figure out all of the best stuff of all your technologies and come up with new sensors. So they are working on themselves on some new imaging technologies, but they are still committed to CCD. They have kept the wafer fabs in Rochester open that are used to make the CCD sensors, and they are in fact bringing out new models of CCD sensors. There will be an announcement, I believe it is next month, of a new sensor which you will find very interesting. It will find its way into our cameras soon. So it's not just Sony going after the cell phone market. There are other companies that are going after different markets, industrial, medical, science markets. So one way or the other, we're eventually going to have CCD sensors and CMOS sensors, eventually all CMOS sensors, that are intended for applications like ours. It's just a matter of time. So the good news is that in the long run, we will have good quality cameras that are less expensive. The downside of it all is it might be a long time before we see a replacement for a 16803 that's in CMOS, because that's a very high performance chip and a very large chip. And it will take them a long time to decide they want to go after that because it's a small volume market. So we'll see. All the companies are saying very promising sounding things. We'll just have to see what they actually do. There are other companies other than Sony and Kodak / ON Semiconductor. E2V is well known for making back-illuminated sensors, and a certain company that's now located in Canada will be releasing a camera with some of these products in sometime next year. They also make scientific grade CMOS platforms. So there is actually astronomy cameras being made today on the CMOS platform by ETV. So in some ways, we're already there. So where are we headed in the future? Well, it's pretty clear that for the time being, CCD and CMOS sensors are going to continue to coexist. And the CCD niche will be shrinking over time to only the most high performance sensors as the CMOS gobbles it out from underneath. And eventually, CMOS will completely take over and supplant the CCD sensors. CMOS, of course, as I said, will continue to improve, and it will supplant CCD entirely, I expect, but it will take years. It may be 10 years before this happens. And so eventually, we should be seeing large format, large pixel CMOS sensor with performance comparable to what we have now on the CCD front. And as I said, this will make it easier to build a high performance camera and therefore less expensive. Now, cooled cameras are always going to be a bit expensive because of all the mechanical gyrations you have to go through to chill out a chip and not have it frost over. So the cameras are still going to be more expensive than a DSLR, but they're going to be they could be a lot less expensive than they are now. A KAF 16803 sensor is almost $4,000 today for the sensor. They need to build a camera. So we could see a big improvement in that. That's an example of a picture taken with a 16803. The actual frame is much larger than this, but wouldn't project very well if I shrunk it. I was asked to give a quick update on SBIG. Now, SBIG started back in the late 80s, early 90s as a company in California, in the Santa Barbara area. So it was called Santa Barbara Instrument Group. And it was formed by 4 amateurs who created the ST4 auto guider for a project, an astronomy project. And then it was a pretty successful product, so they went on to make more cameras, and it grew into the SBIG we know of today. About 4 years ago, the senior partner, Alan Holmes, was thinking about retirement and went to shop it around. And the company was in fact bought by a company called Aplogen, which was a startup trying to make biomedical products. They wanted to use SBIG cameras in their products. They managed to not succeed in launching a biomedical product and basically failed as a company and almost took SBIG down with them. Fortunately, through a series of machinations, somehow we managed to pick them up. So SBIG is no longer Santa Barbara Instruments Group. SBIG is a registered trademark of Diffraction Limited, and we acquired all their assets, their intellectual property, their brands, their designs, their inventory, and all their office furniture, even their staplers. We got everything. We did not get their employees. However, they did. Some of them did stay on board for a while, and I'll explain that in a moment. This is our office in Ottawa. Diffraction Limited incorporated in 1993. Our first product was actually called Quick Fringe, which is for interferogram analysis for optical testing. Our second product was MAXIM DL. We decided to start out doing software products because it's a less expensive way to start a business. So basically started in my spare room with me and a friend sitting at computers typing away, and eventually evolved into a real company. But that was a very inexpensive way to start. I'm actually a hardware engineer by training, but we decided to start on software. Today we have a 10,000 square foot facility near Maryville Road in Ottawa. We have office and engineering space, manufacturing space, warehouse space, and we are currently at 13 staff and growing. I expect to hire another 3 to 4 people over the next 6 to 8 months. So our original products included MAXIM DL, MaxPoint, the Bullwood Cloud sensors, MaxDome, and we had various other OEM products that we made for other companies that you'll never hear about because they sell them under their own brands. Not all the things we make are astronomy related, but much of them are. So about a year ago, October 1st of last year, we acquired the assets of SBIG, and we transitioned the operations to Ottawa over a 6-month period. During that time, we were able to keep some of the staff, of the remaining staff, on board, by having Mike Barber incorporate a little company in California called Santa Barbara Scientific, and then he hired them all, and then we paid him to pay them. So that way we avoided having to operate in California, which would have been stupid expensive for us. Anyway, that allowed us to continue building the cameras during the transition and transition all the technology up to Ottawa. And then about in the May time frame, we loaded up a 53-foot long truck and loaded all the stuff into it and brought it up here. Alan Holmes actually started a new company called Cloudland Instruments. They are making Earth observation cameras for satellites. He hired Linda and Craig, the two engineers. Mike Barber started another little company called Santa Barbara Scientific, the one that was actually kept things running while we were transferring. He's kept that company, and he's now selling a new version of the seeing monitor that is based on an SBIG camera, and he plans to make some other new products. So we've had a couple of spin-off companies result from all this. Bill Lynch is actually started a little company called SBIG Service and Repair, and he is repairing cameras down in, actually he lives in Alan Holmes' office, and he rents a little bit of space from them, and he repairs cameras for us, which is great because he knows how to repair all the old cameras like the ST7s and the STLs and things that we don't make anymore, and we honestly don't know how to fix, but he does. So we were able to retain that. Because we want to keep Bill employed, we send all the repairs to him, with a few rare exceptions of some things that come to Ottawa. So we're now fully up and running. It took a year. It was a year from hell, as expected. Any sort of corporate acquisition always is. But we managed to get everything sorted out. A few of our products are still made in Singapore by a contract manufacturer. We expect to be moving that back to Ottawa over the next year. Most of the products are built in Ottawa. All the big cameras are made in Ottawa. All the AOXs and AO8s and all those things are all made in Ottawa. It's just the small high volume cameras that are made in Singapore. We ship everything from Ottawa. We have an interesting service set up for shipping to the States where we put them all in a truck, send them to Ogdensburg, and then they go into FedEx from there so we can actually ship cheaply. That was a big disadvantage of being in Canada. We've found a way around that. And as I mentioned, Bill Lynch is repairing cameras down in California, literally across the parking lot from where SBIG used to be located. Now that everything is working smoothly in Ottawa, we're now focusing to engineering new products. Of course, it's a time to refresh the product line, add new sensors, and so we're busily working on that right now. We have an engineering staff that's quite capable of designing these. Here's Chris. He's working on a new camera on the CAD software right there. It's a little too early for new announcements because I don't like to announce things before we're quite ready. But one thing I will announce is that we are building an off-axis guider to go with the big SDX cameras. Currently, that's the only camera on the line that still has a built-in guider instead of being a part of the filter wheel. And we're now building a filter wheel guider for the SDX camera. We finished the design for that a few weeks ago. We're waiting for the prototype parts to come in, and so we should have an announcement for that product very shortly, but you're hearing it here first. As I mentioned, we're designing new sensors into our line, so we're including new sensors from what used to be Kodak, as well as sensors from other companies, and that is plural. More than one sensor manufacturer will be used for future cameras. Just going to very quickly go over our current products since we're running out of time, or are we? How much time do we actually have left? Okay, so I'll go over this briefly. We have the flagship cameras, which is the STX. With the STX 1603, we actually have an STX 9000, and we try very hard not to sell them because those sensors have very bad residual bulk image. We've actually sold 2 of them when people said, yes, yes, I know, I really want it. We really try to talk them out of it. We also have the STXL 11002 and 6303. Those are our big cameras. They all look like this. We have the large adaptive optics unit. This is a wonderful machine that was designed by Alan Holmes. The fellow was a genius. I got to say, Alan Holmes is an amazing fellow. This thing is beautiful. It's thin. The electromagnetic actuators are just really clever. Marvelous product. Really happy we have that. We also have the smaller versions, of course, the AO8s, which are driven by motors. This is a much more elegant product, and I actually am thinking once things settle down, we'll make a smaller version of this for the small cameras. Then we have the filter wheels. These are the self-guided wheels for the SDXL cameras. And then the big filter wheels for the SDX camera, which we're going to be adding on a add-on auto guider onto. The middle series of cameras is called STT. This is the evolution of the old sort of round / tombstone shaped ST cameras like the ST7. Currently we have 3 models, the 8300, which is the most popular, the 3200. This sensor doesn't get a lot of attention these days, but it actually is the most sensitive front illuminated sensor I've ever encountered. They're actually really good chips. And the STT 1603, the A08 adaptive optics unit, and again we have smaller self-guided filter wheels for this line. And the nice thing about the big filter wheels is they have this mechanical detente system, so the filter always ends in exactly the same spot every time. So if you take flat fields and there's a dust speck on your filter, it always ends up on the same pixel every time. Our low-end products start with the STF cameras, with the 8300 and the new 8050 and the 4070. They were just launching these when we took over. I actually unlaunched them because I didn't like the way they worked, and we did a redesign, and we have relaunched them. They work much better now. We are about to launch the 402, 1603, and 3200 in STF. Around the time we took over SBIG, we discovered that the boards that were used to make the ST402 series cameras, we couldn't build them anymore. There was an obsolete chip in there you could not buy for love or money. Just not available. So we had to stop making those cameras for a while, and we now have the new boards ready. They've been in beta testing. People seem to be happy with them. So we're going to roll that into production over the next few months. So we'll have the 402, 1603, and 3200 in the small package again. We also have low-cost 5 and 8 position filter wheels, and there is, of course, the built-in filter wheel for the 402. The 402 is a very popular product for universities because they can have the photometric filters built into the camera. It's relatively inexpensive, great for student products and projects and things. And then we have our small SDI camera, most commonly used as an auto guider, but they are very versatile. There's a little spectrograph you can get for them. There's the off-axis guider for the small cameras. And this actually is a focal reducer. People don't know this, but all of our guider units have focal reducers built into them to give the camera more area on the sky so that we can find guide stars more easily. And then there's the Sgi Guider Kit, which turns your SDI into a little mini guide scope, which is quite capable of guiding telescopes up to about 2,000 millimeter focal length. No problem. So that's a very, very popular option. And we have a few specialty products like the all-sky cameras. They're actually very popular. The camera adapters, I was amazed how many camera adapters people want. People love the camera adapters. I did not realize that before. The standalone guider, the SG4, sort of the descendant of the ST4, and then the remote guide heads for the big cameras and the STT cameras. On the software front, yes, we still offer Ccd Ops. We don't have Ccd Soft anymore. SoftwareBisc has discontinued it. The deal that SBIG had with them didn't transfer over as part of the financial arrangements, and frankly, they're a competitor. So we're not distributing the Ccd Soft software anymore, but we are going to replace it with a special bundled version of MAXIM DL. I would have wanted to have it done already, but we've been so busy over the last year, we just haven't quite got it ready yet. We're also in the conceptual phase of designing a new driver architecture. SBIG is currently on the 2nd generation of camera drivers, and we actually want to take it to a new generation, start with a clean slate, and make a camera driver architecture that can evolve in the future much more easily. And it will have both a direct API and native ASCOM support. As you know, we're big proponents of ASCOM. So, any questions?
First of all, Doug, I want to thank you for this very informative conference. But my questions are going to go like customer service. I currently own a ST7, ST8, ST10, which of all are XME cameras, an A08, and an SGS spectrometer. So I'm keeping my fingers crossed because I don't want two cameras, you know, to get into trouble because the customer service about these parts are like a wild goose chase.
Right.
As far as I'm concerned, the ST10XME is one of the better cameras that Santa Barbara built. So I'm just wondering why there aren't any parts. You know, if it goes, I can't do anything about it.
Yeah, if I had been running SBIG back when the decision was made to transition to STT, I would have stockpiled parts because they were still available or just starting to become unavailable at the time, and that's one of the reasons why the line was discontinued. It was a case of either redesign the circuit boards or go to the new platform they were already working on. I think they made a big mistake in not stockpiling more parts. I can't solve that problem because all these parts we can't order. However, since we've taken over, we have ordered the most common part to fail on an STL camera, for example, is a little switching power supply that's in there. We have got a bucket of those now. We were able to track down a supply of those when we bought those. We're doing the same for ST7 series cameras to some degree, but it's much harder. Bill Lynch has what he calls a graveyard of broken ST7 series cameras, and he will harvest parts from them if he needs to get a camera back up and running. So as long as certain components that we really can't replace don't fail, he probably can service the camera, but it is getting harder.
Well, I actually talked to him about 6 weeks ago. I just wanted like a 1800 lines grading. He says, I can't find any, there's none. So we have to go to a wild goose chase on the internet to find replacements for those or buy something we haven't got yet. I have the 25 and the 100 micron gratings, but the 1200 and 1800 are just simply unavailable from Santa Barbara.
Yes. For most of the products, we have the original parts bill of material for them. Okay. And if you call us up, we can actually tell you what the manufacturer of those units was and what their part numbers were. And so you could go to the manufacturer and try to acquire them yourselves if they still make them.
Okay.
If they don't still make them, then yeah, I'm sorry, but
no dice.
Okay.
Since I understand CMOS pixels can be read independently, can we imagine a camera with only one detector, one chip, but you could use any star in the field of view to guide? In other words, that star would be sacrificed, but you would need only one chip. You would have the choice over the old field.
Maybe. The limitation is that, while in theory the CMOS cameras can do this, in practice they have a certain design architecture that for how they design the chip, and most of them are designed either for rolling shutter or that sort of thing. And the built-in logic in the camera doesn't do those sorts of things. Some do, but as far as I know, most of those aren't the ones that do the super high performance. So it's really going to be a wait and see what kind of capabilities these chips will have when they finally reach the market. It may not be suitable for what we're doing. And also remember that whenever you run electronics inside of a sensor, they tend to emit light in the process, and it can contaminate your image. So there is downsides to doing that sort of thing. It also makes heat, which can also affect the regulation of the temperature.